Hi guys, welcome to my channel. Why it is so difficult to predict a stock price? Every day, millions of investors analyze earnings, economic data, interest rate and market trends. Yet tomorrow's stock price often seems surprisingly unpredictable. Why? Because many financial variables behind lies something called a random walk. A random walk is one of the most important concepts in quantitative finance because it challenges a common assumptions. Thus, the past value always help us predict the future. Today, we will explore why random walk are different from normal stationary time series, why a concept called the unit root matter, how economists test for it using the Dickey-Fuller test, and how analysts transform non-stationary data into a form that can actually be modeled. This is a foundation for understanding modern financial forecasting. So let's start with a fundamental questions. When we observe a financial variable today, how much information does today's value give us about tomorrow? For some variables, the answer is a lot. For example, interest rates often show persistence. If rates are high today, they may remain relatively high tomorrow. But for other variables, especially some asset price, the past may provide very limited information. The next movement may depend mostly on new unexpected shocks. This idea leads us to the concept of a random walk. A random walk is a process where the current value equals the previous value plus a random, unpredictable change. The important insight is the best forecast of tomorrow may simply be today's value. The simplest random walk is written as xt equals xt minus 1 plus epsilon t. Let's break this down. Today's value equals yesterday's value plus a random error term. That error term represents everything unexpected. News announcements, economic surprise, investor sentiment, political events, anything that cannot be predicted beforehand. The assumptions about the error term are important. First, the expected value of the error is 0. This means positive and negative shocks balance out over time. Second, the variance of the error is constant. The size of shocks remains stable. And third, the errors are not correlated with each other. A shock today does not tell us anything about tomorrow's shocks. These assumptions create a process where changes are random. Now, sometimes random walks include a predictable directions. This is called a random walk with drift. The equations become xt equals b0 plus xt minus 1 plus epsilon t. The difference is the constant term. The drift term creates a systematic upward or downward movement. For example, a country's GDP may generally increase over time, but yearly changes still contain unpredictable shocks. The drift captures the long directions, the random error captures unexpected fluctuations. So we had two versions, a simple random walk, no predictable movements, and a random walk with drift, a predictable average movement plus randomness. Now let's connect random walk with our previous discussions of autoregressive model. Remember the AR1 model? A stationary AR1 process requires P1 lower than 1. Why? Because the effect of past value must gradually disappear, but a random walk has P1 equal 1. The previous value has a permanent effect. A shock today never disappears. It becomes part of all future values. This creates what we call a unit root. A unit root means the autoregressive coefficients equals 1, and this is the key reasons random walks are not covariant stationary. So, think about dropping a stone into water. In a stationary process, the waves gradually disappear. The system returns toward equilibrium, thus mean reversions. But in a random walk, the shock permanently changes the level of the series. The system does not return to a fixed average. For example, suppose a stock price randomly increased by $10 because of unexpected news. Under a random walk assumptions, that increase becomes the new starting point. The price does not automatically return to where it was. This is why random walks have no finite mean reverting level. So let's compare the two ideas. A covariant stationary process has three important characteristics. First, a constant mean. The average level does not change over time. Second, a constant variance. Volatility remains stable. Third, a constant covariance structure. The relationship between observations and different logs remains stable. A random walk violates these conditions. It means change its variance grow over time and shocks accumulate abundantly. This distinction is critical because many statistical models, include AR models, assume stationarity. Using a non-stationarity series without adjustment can produce misleading conclusions. So, how do we determine whether a time series has a unit root? There are two common approaches. The first is estimating an AR model and estimate residual autocorrelations. If the model is systematic pattern in the residuals, the specifications may be incomplete. However, this approach is less precise. The more common method is the decay fuller text. This text directly examines whether the series contains a unit root. The decay fuller text begins with the AR1 model. Xt equal B0 plus B1 Xt minus 1 plus epsilon t. Then we subtract the Xt minus 1 from both sides. The equations become then the Xt equal B0 plus B1 minus 1 Xt minus 1 plus epsilon t. Now we define G1 equal B1 minus 1. The entire text focus on whether this new coefficient is 0 or negative. Why? Because if B1 equals 1, then G1 equals 0, which means there is a unit root. The hypotheses are null hypothesis. The series has a unit root. Alternative hypothesis, the series does not have a unit root. So, the text statistic is Tf equal G1 over Xg1, where Xg1 is the standard error of the coefficients. The decision rule is slightly different from a normal t-text. Because of the special property of a unit root testing, we use modified critical values. If the Tf statistic is sufficiently negative, we reject the null hypothesis. That means no unit roots. The series is stationary. If we fail to reject the null, the series remains non-stationary. Now let's say the decay fuller test confirms that the series has a unit root. What can we do? We transform the data. The most common method is called first differencing. Instead of modeling the level of the variable, we model the change. The first differencing is then the xt equals xt minus xt minus 1. For random walk, xt equals xt minus 1 plus epsilon t. Subtracting the previous value gives then the xt equals epsilon t. The random walk disappears. What remains is the random shocks. Because the errand term has constant mean and variance, the transform series become covariant and stationary. This is one of the most important ideas in financial econometrics. Before predicting the future, understand the structure of the past. Thanks for watching.